This video is presented by Professor Gottapu Sasibhushan Rao. In this part, we will understand why sound waves are preferred to radio frequency waves for underwater sensing. The main reason is the electrical conductivity of seawater. We will see how seawater causes strong RF attenuation, how this effect is described using attenuation constant and skin depth, and finally why sound waves are much more suitable for sonar applications. Seawater contains dissolved positive and negative ions. Therefore, it behaves as an electrically conductive medium. When an RF electric field enters seawater, these charged ions are forced to move back and forth. This motion produces a conduction current. As the ions move, part of the electromagnetic energy is converted into heat through Joule loss. Therefore, the RF signal continuously loses energy, and its electric field amplitude decreases rapidly with distance. The equation shown here represents this exponential decrease. So, the conductivity of seawater is the basic physical reason for strong RF attenuation underwater. Transition. Now that we know the physical cause of RF loss, let us look more closely at how this energy is lost. This figure summarizes the energy loss mechanism. The RF field first supplies energy to the charged ions present in seawater. The movement of these ions produces conduction current. This current dissipates part of the RF energy as heat. As energy is continuously lost, the propagating RF field becomes weaker and weaker with distance. That is why ordinary radar and microwave frequencies have only a very limited useful penetration in seawater. Transition. To measure how rapidly the RF field decreases, we use the attenuation constant and the concept of skin depth. The electric field amplitude of an RF wave decreases exponentially as it propagates through conductive seawater. Here, alpha is called the attenuation constant. A larger value of alpha means that the signal decreases more rapidly. For a good conductor, attenuation increases as frequency and conductivity increase. Another important quantity is skin depth. Skin depth represents the characteristic distance over which the electromagnetic field penetrates into the conducting medium. Skin depth is inversely related to the attenuation constant. Therefore, when frequency increases, attenuation increases, skin depth becomes smaller, and RF penetration becomes poorer. This explains why high-frequency radar and microwave signals cannot travel very far through seawater. Now let us directly compare RF waves with acoustic waves underwater. On the left, ordinary RF or radar-type waves are strongly attenuated by conductive seawater. Therefore, their useful underwater range is very short, and a distant target may not produce a detectable return. On the right, sound waves can propagate over much greater distances at useful sonar frequencies. These acoustic waves can reflect from underwater objects and from the seabed. The returning echo can then be used for target detection, range measurement, and tracking. Therefore, underwater navigation and sensing mainly use sonar rather than ordinary radar. Let us summarize the important equations. The propagation constant has two parts: the attenuation constant alpha and the phase constant beta. For conductive seawater, the attenuation constant becomes larger when frequency or conductivity increases. The RF electric field then decreases exponentially with distance. Skin depth is the reciprocal of the attenuation constant. At a distance equal to 1 skin depth, the electric field amplitude falls to about 37% of its original value. After a few skin depths, the RF signal becomes extremely weak. So, conductive seawater produces strong attenuation, rapid exponential decay, and very small penetration depth. Therefore, ordinary radar and microwave signals are not suitable for effective underwater propagation. Thank you.